Yes. So I will show you a live demonstration of the VERMEER rodenticide tool. And I will just remind what I had presented yesterday for introducing this case study. So VEGA-HUB published quite recently a document with different emission scenarios regarding rodenticides. And in this document, they describe a scenario concerning the release of rodenticide in surface waters. And they ask the question about secondary poisoning. The problem is indeed to know how some organisms can be contaminated by rodenticides like fish or aquatic mammals. So the objective here is to simulate this kind of aquatic food web, so to know to what extent rodenticide can contaminate different organisms in the aquatic system, like phytoplankton, invertebrates, fish, and even aquatic mammals like otter. So what I will now show is a concrete exercise based on this kind of food web relationship. So I will change here. Sorry, perhaps I have to move and to go directly to the Merlin Export tool. Do you see? Do you see the Merlin Export tool?
Yes,
Yes,
yes.
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 Okay. Okay. So we will build together this kind of exercise of case study based on the ECA scenario. So first, you can see here an information window when you can here described the work you are doing if you want to communicate this work to other colleagues, etc. For example, here test demo, uh, you you describe the test demo you are writing, and you can describe it demo for VERMEER workshop, etc., etc. And you can write what you want if you want to communicate different information to colleagues, what you have actually included in your scenario, etc., etc. Okay, so here you have a description of your scenario. You can move now on the model window. So this is the predefined scenario we have prepared for this case study. In this predefined scenario, you can identify different blocks. So the river, phytoplankton, invertebrate, fish, mammal blocks, which will be used for simulate the exposure of organisms in the aquatic system. And also a block on ecotoxicity, which will contain different simulation about ecotoxicological endpoints like ecotoxicity for Daphnia, for fish, for algae, etc. Between all these blocks, there are some relationships. For example, phytoplankton can be eaten by fish here. So in this block here, in this relationship, there is the prey-predator relationship implicitly. So normally you have nothing to do on this window because the scenario is already prepared for you. If you want to know more about the content of the models, you can open here the models, for example, the mammal models. You can identify the different compartments included in the mammal model, for example, blood, muscle, liver, kidney, milk, etc., and all the relationships between these different organs. If you want to know more about the equations which are included in the model, you can click on blood, for example, and here on the right part of the window you have information, and you can read the equation. Obviously, it's not so easy to read, but if you take time, you can rebuild the model from this information window, so it's quite transparent. Normally, you have nothing to do on this window. Obviously, if you want if you do not want to simulate concentration in mammals, you can click right and disable this block here. You see that the mammal now is disabled. That means that you will not simulate any contamination in mammals. So you can choose the blocks you want to use in your own scenario. So I will now enable this block. On the context, you will choose the different substances you want to test, and you can build the food web relationships. So here we have prepared a list of rodenticide commonly used and recommended in regulation. For these rodenticides are described by their ECAS number and also by their smile here. You see smile here. Okay. You can select all the substances. So this is here, this is the available substances, and here, this is the substances selected for simulation. So you can select all the substances or 2 substances, for example, for your simulation, if you want to compare brodifacoum and bromadiolone, for example. You can add a new substance if the substance you want to test is not in this list. You can create a new substance, new compound. You write here its name. And you have obviously to define its smiles, because the new compound will be identified by its smiles, and the tool can be parameterized thanks to these smiles. I will not add a new compound now, but it's quite possible. So this is the first choice you have to do. Secondly, we have prepared, predefined a typical food web with 1 species of phytoplankton, 2 invertebrates, pelagic, benthic, and 4 fish species, small pelagic, small benthopelagic, small carnivorous, and big carnivorous, and 1 mammal species, otter, for example. It corresponds to the picture I have shown at the beginning of this presentation. If you want to add a new species, you can choose here, for example, mammals, and you add a new mammals here. For example, if you are in a marine system, you can add a dolphin, and this is a new organisms you can define. Or you can also remove. So you select here, and you remove the species which are not relevant for your own scenario. So once you have done this, your own scenario is defined. You have chosen the substances, you have chosen the organisms you want to simulate. There are some options for running the simulation. For example, here, about suspended particulate matter in the river, you can have some measurement, and in this case, you will enter directly the measured suspended particulate matter. If you have no measurements, the suspended particulate matter will be calculated through a model. The same for the concentration of chemicals in raw water. You can have some monitoring data, and in this case, you enter your own monitoring data about the concentration of chemical in river water. If you have no monitoring data, you will calculate the concentration of chemical in river water using data about the releases, for example, industrial releases or urban releases in the river. This can be done for all the substances or for each substance individually. For example, for body vacuum, you can use calculated, and for bromadiolone measured, for example. Okay, I will change. And here, default is for all. Next step, you have to define some time series. For example, the temperature in river water. In this case, we have chosen a constant temperature in river water because it corresponds to the VEGA scenario. But you can obviously change this time series. For example, here, about measured suspended particulate matter, we have chosen a constant suspended particulate matter concentration. But if you have some measurements in your own water, for example, here, I have some measurements about flow rates. I don't know if you see my Excel file. But I can copy and paste here a new monitoring time series about suspended particulate matter, okay, instead of a constant one. So in this, and you can do the same for the flow rate of the river, for example, concentration in raw river water, etc., etc. So I will go again on the constant on the basic scenario here. Next step, parameters. For running the simulation, you need to define different parameters. These parameters are classified. You have here the physicochemical properties of the chemical, parameters related to the river, for example, depth of the river, width of the river, the fraction of organic matter in suspended matter or in sediments, half-lives of the compounds in water and in sediments, etc. Parameters related to phytoplankton, for example, lipid fraction of phytoplankton, on invertebrates, on fish, and on mammals, and ecotoxicological data also. For example, about fish here, you have to define the fish diet preference for food items. Remember that I have defined here 4 fish species, and for each fish species, you have to define what is its food preferences. For example, here, the carnivorous bentopelagic fish species eats invertebrates and small fishes. So this is the proportion of food for this carnivorous fish species. So this is the matrix for food predator relationships. Some parameters are dependent of the chemical. I will choose two chemicals only for facilitating the demonstration. So this is the case for the bioconcentration factor. So this is the relationship between concentration in the organisms and concentration in water. Let's imagine that you have no data in this for this parameter for these two substances. This is the case, for example, when you add a new compound. You can generate the parameter values for this parameter and for these substances through the VEGA model. In this case, you directly open the VEGA library, and so the system will recognize the relevant models available in VEGA. VEGA will run the models, the relevant models, and will return a model prediction for these parameter values. And so in this case, you can choose the values simulated by VEGA. And in this situation, your model is parameterized. For the same parameter, you can also, let's imagine we have nothing here at the beginning. You can also generate the applicability domain index. So you just click on VEGA, and the applicability domain index will be returned here. It will be used for measuring the reliability of the VEGA prediction. So you can use different VEGA models directly for all the parameters which are indicated with the VEGA here, the signal here in front of the name of the parameter. So in this case, the model is parameterized. Let's imagine that you have something empty here. When you want to run the simulation, it will indicate an error here. It indicates that the bioconcentration factor is missing. And in this case, you have to generate a value for this missing parameter. If you have no indication of errors, that means that you are able to start the simulation. For the simulation, you can choose different options: deterministic, probabilistic, and sensitivity analysis. We will start with deterministic. Deterministic means that for each parameter, we have a default value, one unique default value. You will choose some options for the simulation: the start time, the end time. For example, here, I want to run the simulation over 1 year. And you have to choose also the kind of outputs you want to generate. For example, here, from start to end with 1 increment, that means that I will see the results each day for 1 day increment. But I can change this. You can choose to see the result each 10 days, for example, or etc. At this point, I am ready to run the simulation. So I just click here, and you see that the simulation is finished 2 seconds about. The next step is to visualize, to see the results. So in this case, you have results for different blocks: river, phytoplankton, invertebrates, fish, mammals, etc. You can select the output you want to see, for example, concentration of the chemical in fish. And you select here the fish you want to see and the compound. For example, if I want to compare Brodifacoum and Bromadiolon in small pelagic fish, I can select here the 2 compounds for this organism. And if I want to see the results for big carnivorous fish, I can select this. Or I can compare different organisms for the same compound. Here, all fish species for body vacuum. Obviously, you can see you can do the same for all the outputs in the system. For example, for mammals, concentration in blood, kidney, liver, milk, muscle, etc. If you want to change something in your simulation, you can here create an archive. For example, here test 1, and I can change one parameter value or one value for time series. If, for example, here I had chosen a value for suspended particulate matter, 100. If I do 1000, so I increase the suspended particulate matter, I can run again the tool, and I can create a new archive, test 2. I can compare the effect of this parameter for a given output. For example, concentration of the chemical in water, in fish. You can compare the results for test 1 and test 2 and see the effect of this parameter value. I will. This is the first option for running the simulation. There is another option which is probabilistic. Probabilistic can be used for running uncertainty analysis. Indeed, each parameter can be defined, but its best estimate value, default value. For example, here I take the example of a fraction of organic matter in suspended particulate matter. The default value here is 6.6%. But if this value is uncertain, I can also define a probability density function. For example, here, this is a log normal probability density function. That means that the best estimate is 7%, for example, but I can't exclude that the organic fraction is 2% or 15%. So I define this probability density function. I can do the same for all the parameters. Okay. For example, lipid fraction, not this one, but any parameter, for example, in sediments, etc. In this case, if I want to estimate the uncertainty of the prediction, I can use the option probabilistic. And I will define the parameters I want to include in my uncertainty analysis. For example, here I have selected all the parameters for which probability density function was defined. I also define the number of simulation I want to generate. What does it mean? It means that the system will randomly select one value for each parameter. The system will run the first simulation and will return the results. And the operation will be repeated a given number of times. For example, here I can choose to repeat the simulation 10,000 times. So for a question of time, I will choose 1,000 times. So it will generate 1,000 random simulations with all the uncertain parameters. So in this case, I can start the simulation. Obviously, it takes more time because it will run the model 1,000 times. So the simulation is finished. And in this case, I can, this is the old one, I can, for example, see the results for fish concentration of chemical in fish. This is the mean the mean simulation, but I can also see the 95 percentile, for example. So this is the conservative simulation, the simulation with the pessimistic parameter values. So in this case, I can see the best estimate simulation, but also the simulation with parameter values which gives the higher possible concentration in fish tissues. And finally, you can also run sensitivity analysis. In this case, you want to know which parameters are responsible for the uncertainty. So you want to identify the most sensitive parameters. You have different options for running a sensitivity analysis. You have different methods here. I have no time to define the different methods. For example, you can select IFAST, and you can select the different parameters you want to include in the uncertainty, in the sensitivity analysis. In this case, if my target is fish, I can exclude all the parameters related to mammals. And I can run again the simulation. So the system calculates automatically the number of simulation required for doing this sensitivity analysis with the IFAST method. So it takes time to return some. So this is the new simulation here. And for example, for concentration in fish, you can here generate different kinds of charts. For example, this one, where you can identify the most sensitive parameters. For example, here you identify that the log KOC here is responsible for a great part of the uncertainty of the model. And you can obviously see here, I have defined the 10 most sensitive parameters, but I can also choose to see the 20 most sensitive parameters. And you see the ranking of parameters in terms of sensitivity analysis. I will run again a deterministic calculation. I have shown all the results with charts here. But you can see exactly the same results in a table format. For example, here, the concentration in fish according to time. And you can export these results in Excel to work on your on this data to build the pictures you want, etc., etc. You can also generate reports which will describe all the features of your scenario with the parameter values, the time series, the results, etc. This is an automatic PDF report which summarizes all the features of your scenario. So I think that I have shown the main options of the tool. Obviously, the same tool is also available for solvents. So this is quite similar. On the list of compounds is different, obviously. And just after, Arthur will show the same result, the same tool with dispersant, which is quite similar also. So thank you for your attention. If you have some questions.
Thank you. Yeah,